Hello and welcome to a new video. My name is Herwig Juster and today we discuss 5 important injection molding design considerations for designing better plastic parts. Follow these moldability guidelines for plastic parts and you can avoid problems occurring during manufacturing and also reduce the overall costs of your parts. Okay, let us get started with the first consideration. This is uniform wall thickness of your plastic parts. So here in the pictures you can see different situation of wall thickness. For example, we have here the worst case scenario on the left, thin to thick. So we gate here and inject here, and here we have the flow. We have a thin section and then which turns into a thicker section. It's the worst case we can have, and we have to avoid. Also very bad is when we have from a thick section to a thin one, as shown here. We gate also here in the center, and more a bad scenario is also too thick to thin like previous. However, here we have already some corner and some radius, so it's a better flow. It's already better. So now we have the worst, very bad and bad scenario. So how is the standard and the best? So standard is uniform thickness, as is already the first point here shows us, where we have no jumps in thicknesses of the walls. And the best is when we have a thin base layer where we inject on, combined with ribs to get the stiffness. This is also shown here. So we have here the base plate and here then the ribs. What are some general guidelines for wall thickness? For reinforced plastics, you should be between 0.75 millimeter to maximum 3 millimeters. When you have unfilled polymers, you can go a bit thinner, 0.5 millimeter is feasible, and you can also go into the thicker direction to 5 millimeter. So this is the general guidelines for uniform wall thicknesses. Then, second design consideration is the rib design itself. We already, in the uniform wall thickness in the previous point, we already touched on this. When you look here in this example, we have a base plate with 2 ribs, and these ribs are 70% of the thickness of the base plate, and they have 4 times the height of the wall thickness here. So this is already a good guideline for you to follow. Here on the other hand, we have no ribs, it's just a base plate. It's the wall thickness is 30% thicker compared to this example here. And when you look in the overall manufacturing and material consumption, this part with no ribs consume approximately 15% more material, and also due to the thickness, because it goes into square with cooling, we have a 70% longer cycle time than with the thinner part with ribs. So it's always better to have thinner base plate and get the stiffness over ribs to have a better manufacturability, moldability, cycle times, and also material consumption. What happens if we use ribs which are thicker than 70% of the wall thickness? Then the material tends to draw away from the center of the opposite wall when the rib cools down, and then you have internal voids or these sink marks opposite of the rib. So this we have to avoid, and usually you can use, if you need ribs which are thicker than 70%, you can also use, for example, more impact modified materials. They can reduce these internal voids also. Rib thickness less than 70% of the nominal thickness is perfect for unfilled polymers. So you don't need even to take the 70%, you can go thinner. Okay. Radius. So it's the number 3 for design consideration. So when we have here, as shown here, a U profile with no corners, no radius, we will have a stress concentration in these areas. The part will be not stable. It's it's all over not good. However, when we add here some fillets, so we remove the sharp corners, we can reduce the stress level of the part. So in general, the fillets you can to maintain now the same thickness around the corner. The fillet should on the internal corner is set to 50% of the wall thickness, or as a general guideline, the corner should be in the range of 0.9 to 1.2 times the nominal thickness of the part. Then the fourth point for proper design is the draft angles on the ribs itself. So we discussed already ribs. However, for ejection, it is important to that you can get the part out of the machine in a proper way. And in the left case, we have no draft angles, so no degrees of wall thickness change. So it's harder to remove then the part on, because it shrinks really onto the cores of the metal cores of the mold. So with draft angle here and here, it is then easier when you imagine to eject the part, because it's forced off the cores. Generally use a minimal draft angle of 0.5 degree to however, it's for most material, the draft angles are between 1 to 2 degrees, depending on the material supplier recommendation. When you have rough and texture surfaces, you need some more additional draft. So the rule of thumb is to use 1 degree of draft per 20 microns of surface roughness additionally. When you use glass filled or low shrinkage material, then the draft angle should be increased. And if you use highly flexible materials such as soft PVC, then you can also decrease it, because it's easier to eject. Okay, the last point, number 5, undercuts. So here in this example you see 4 typical design features. We have here a window in a side wall. We have a overhang above the bottom of the wall. We have a horizontal boss here, and we have a snap finger. So undercuts is everything which prevents the proper ejection of the part, and if possible you have to avoid them, since you need much more complex mechanism in the design and on the machining of the part. Of course, we have also functional undercuts. What we have here, the horizontal boss and also the snap fingers. So, of course, when you need a snap finger, you should implement it and not design it away. But overall, most engineers are not so aware of undercuts, and it also shows to increase the awareness that when you have the part designed, however, in the mold, it can immediately increase the complexity. Okay, if you want to have more information on polymer engineering topics, I highly recommend you my blog, findoutaboutplastics.com, as well as my online courses on polymer material selection. I will link you both the blog and the online courses in the description below. Okay, which video to watch next? In this video, I show you my 5 best online sources for material property data search, which can guide you for material selection. Okay, thank you for watching, and do not forget to subscribe and smash that like button. Till next time, bye.